Buongiorno. Welcome everyone to Italian C++ Conference 2021. I look forward to spending a wonderful Saturday with you all talking just C++. And I'm looking forward to a great agenda all this day. So let's get started. First of all, a few logistics. We're using Remo as an online conference platform. And if you have any questions during the presentations, I encourage you to use the Remo Q&A tab or just use the chat. People over there will pick up questions and we'll look into the platform and try to address questions. If you have any questions or comments during the presentations, feel free to just write them down. I'll try to pick up questions as we move along. If I have a natural stopping point during the particular section of the presentation. If not, I'll defer questions to the end, but I'll make sure to answer all questions. And as always, I'll be around almost the whole day throughout Remo at some table. You can just look for me and maybe we can pick up the conversation over there if you have more things you want to chat about. Or maybe if you prefer to have a discussion that's offline and it's not recorded, that would work excellent as well. So some of you might probably know me. I've done conference talks before, and some of you might be using, for example, tools that I've built over time. I'm going to plug my pet project, Clang Power Tools here. If you're interested in increasing the code quality and finding bugs in your projects, leveraging LLVM tooling on Windows, this is a great way to start. And it's a free and open source project. So that's my plug for today. And now we'll move on to more serious things. We're going to talk about my quest for a better crash. And we're going to analyze some code. We're going to see some real nitty-gritty parts of the runtimes and the behaviors of operating systems and in the ways you can deal with crashes or exceptions or hardware violations. So this talk will have basically three major parts: constructing and remembering crashes and archiving crash information, and for later analysis. Then we're going to see how we can implement such an infrastructure from scratch, and what are the advantages and what secret powers from the C runtime that we can leverage to mine all this information that we need when debugging issues, especially remote issues. And towards the end, we're going to discuss future developments and standard things to come to C++ to address some of these issues, not all. Largely, this presentation is Windows-specific, and even more so architecture-specific, focusing on x86 and x64 architectures. There are obvious things that can easily be extended, for example, for ARM. And we're going to talk for sure about standard developments in ISO C++. I'm going to talk about the P881 proposal that will address some of the issues I'm going to present in this talk, mainly about StackTraces. So we're going to gradually move from Windows domain and exploring these concepts and how to roll our own, and we're going to move towards a standard way of leveraging this information and power. So remember the crash. I think we've all been there, more or less, seeing something like this, or maybe some of you remember our old friend, Dr. Watson, or the modern incarnation of Dr. Watson, that is Windows error reporting, which is a much fancier user experience, basically surfacing the same information. That is, when a process fails, a way to get back to a crash dump and see the core dump and the fault that happened, and a way to archive it for remote exploration. All right. But where do all these crashes go? Because you kind of have a feeling of facing these issues on the client side and seeing things happen to your application or to other applications. But how does all this information being aggregated, and what does it happen? And a few years back, I had questions like this way before we had any app stores or dev centers or any smart portals that you can easily configure to aggregate and archive all this crash information for you to explore. So way back before we had any of these fancy features, cloud features, I had questions like, is this functionality like core dumps and Dr. Watson available for third-party Windows applications, or is it just reserved for Windows components? How can we register for such crash dumps? What does it cost? What does the crash data look like? Who owns it? Where does it go? So basically, I just wanted this. I wanted a StackTrace and the core dump for my process when it fails, and I want a means to get context, rich context information about what happened, and debug issues remotely and asynchronously. The answers turned out to be complicated. Basically, you needed some way of custom registration for each app version. You needed ways to integrate with the Microsoft Symbol server, deployed either on premise, or you had to configure symbol stores, and it basically boiled down to a DevOps nightmare. So rather than being something that as a developer you can easily leverage in your tool chain, it was something more geared towards a complicated setup that was more on the DevOps side. And although it could be done, it turns out it was more complicated than necessary, and most teams steered away from this route. So, of course, like any good programmer, I decided to build my own. And the goals were quite straightforward. It had to be quick to develop, easy to integrate in our CI/CD, so no special servers, symbol servers, or anything. It had to have a zero footprint on the client side, so no way of shipping symbols or anything like that, because symbols can be very large for some applications, including our own. Zero performance impact on release binaries, so you don't want to pay anything on the happy path for having this functionality built in. And easy to use as a standalone tool on a non-dev machine, for example, for processing crash reports and triaging them. So you don't want to have developers only access to this information in order to triage issues. You want to be able to have support engineers able to receive this information, catalog it, and triage information into bug report systems so that it can be addressed offline by developers. So the workflow we geared towards was something like from a build system, with each build, you get your build artifacts that you archive. So alongside with these artifacts, you have additional payloads that you need to cache in order to be able to leverage this functionality deferred. So along with each commit, let's say we have a particular Git commit, you would have a symbol archive, which is to be expected. This is this DSYM file here. And you have the standalone tool that I mentioned earlier that we've built to help explore these crash reports and associate them automatically with each symbol archive. So a symbol archive for a release build, for example, a very small one here would have here PDBs for the binaries that we built in this particular build commit. So it's basically a fancy zip bundle that contains all these PDBs, so debug databases, and this can be very large. You can see here they can gravitate it towards the gigabyte size area for large binaries, and you need to compress those because as it turns out, PDBs are fairly they compress fairly well, so you conserve lots of disk space this way. And one important fact is that you do need to build full debug databases. Older versions of Visual Studio actually introduced the concept of debug fast link, and it was a way of building incremental PDBs in order to speed up the dev cycle for debug builds. And that was great at the time because you got quicker dev cycles. But for release builds, it's actually essential that you construct full PDBs instead of a collection of incremental PDBs for each incremental build that you perform. So although there are tools in the Windows SDK to merge incremental PDBs into a final full PDB, that workflow is cumbersome and it's better avoided. So, and nowadays with the latest versions of Visual Studio, for example, VS 2019, debug fast build actually debug full. So building the full debug PDB actually got way faster. So we don't see any need to actually use debug fast link anymore because the building full debug information actually got very fast. And for release builds, those are the ones that you archive symbols for those builds. You actually have no benefit of actually using fastlink anyway. So the secret here, the secret sauce is archiving your project PDBs. The reason this is required is because, and some people may not be aware of this fact, actual builds are not fully deterministic. So each time you build an application, although you might be building the same git commit, the same tag, for example, the actual binary bits that get outputted are not the same each time you build it, because there are things like timestamps that get involved into these final bits that the tools output. So in order to be able to actually debug to a particular crash dump from a particular build commit or a particular release tag, you actually need the very same build artifacts, the very same debug information and PDBs from that build. So that's the reason that you need to archive all this information, because you basically have two choices. Either archive these build artifacts, the PDBs, for example, or find a way to produce deterministic builds each time. In this, I have to mention this, it can be done. There are some projects out there and some resources in helping you to produce with this issue is present with LLVM and MSVC as well. And there are resources helping you to achieve a deterministic build each time. So, for example, if you go to a particular git commit, you would have each time you would produce the bit identical binaries. But the process is not straightforward. It's not quite easy to implement, and it's not something that any project might choose or any team might choose to actually implement themselves. There are benefits to it, but most teams don't use it. So the easier route here, as I said, the goal was to build something that's easy to deploy. The easier route here would be just to archive symbols. And you don't want a dry StackTrace crash report that is without symbols. So you want rich information, and that's why you need to keep everything. So and sometimes even with the right symbols, things might be very, very puzzling. So drilling down into a particular StackTrace might not give you all the context information that you might require to be able to start drilling down and debugging a particular issue. So symbols are not the answer to everything, but it's a good start. And we're going to see how we can build this contextual information and get a way to start debugging a particular issue later, deferred, so not at the moment it occurred. So the simplest workflow would be that you would have a particular crash in the application. A crash report without symbols would be sent through a channel to a support service automatically to be collected, symbolicated, and triaged. And then you would have some standalone tool that you can use to basically rehydrate this crash dump with all the rich symbol information that you have archived on your servers. So we select a particular build with a particular revision. The associated build artifacts can be automatically located via build tag, and then you could get this resymbolicated StackTrace that you can jump in and work through. So bug fix and rejoice. So you basically end up with something like this, where you have all sorts of information here. We're going to drill down and see the important bits in what we have to deal with here. Right away, we have our first clues into what happened. We have an AV, we have an access violation here happening, and we can see it was an access violation through a write through a null pointer. So right away, we have some information to steer us towards the problem. We have the faulting address, and we have the context, the StackTrace for what happened. We can see the function, source file, and line number, and we can see the path that was reached to this point, so we can drill down and see what happened there. We're gonna focus a bit on how it works, and I think there's plenty of good things that we can learn about how things work underneath. And although you might be satisfied to just using a framework like this to just solve the problems and fix the bugs, I think there's great value in understanding how it works behind the scenes. So we're going to drill down on this. First of all, we have to address the elephant in the room, which are structured exception handling. If you work on Windows, I guarantee you should worry about this, and you should care. So not all projects use async exceptions on all modules, or it's basically the same name, async exception or structured exception handling. Or I've put some links if you want to read more. The reason this is important is because, and this is where the project setting where you can enable them. There are various incarnations in terms of either configuring it through ls build or project configuration files, or command line switches, for example, if you're dealing with CMake scripts or some stuff like that. So I've basically put all the forms in which this might be interesting to you, depending on how you build your projects. The reason this is important is because you want to be able to handle C-structured exceptions as C++ typed exceptions, and be able to, for example, if you want to record and pinpoint issues like that access violation that I showed earlier, where you've seen that it was a write through a null pointer or write through a dangling pointer or something like that, you if you want to see that kind of rich information, you must be able to tap into this SEH mechanism in the Windows runtime, so that you can translate all this information and archive it, either to log it or send it to a crash service, or use it later to debug offline. So there are hooks in the C runtime that are provided to help with this issue. For example, one such API that we can use is SC translator, where you can provide a callback that you implement, and this callback, we're going to see how it translates all this information from the operating system into actual digestible information for a developer. And another thing, when dealing with exceptions, sometimes they might escape the enclosing context and the enclosing stack frame, and there might not be an exception filter or handler somewhere down the path during the stack frames. So you have to have a way to have like a catch-all somewhere where you can basically trap all unhandled exceptions that might try to reach outside of your process. So if an exception occurs that it's unhandled anywhere in the project, you have a ways of intercepting it. And again, you can provide a callback where the runtime will call this this function you provide in case some exception might escape your context. For example, this is how the callback would look like. You would get this exception pointer structure, and we're going to see more about what's inside there. It's all the contextual information about what happened lies within these structures from the SDK. So, for example, we can see right away we have an exception record there, we have an exception code, the exception address, and right here we basically extract this context record and compose a friendlier message, a richer message that contains even the StackTrace from this context record. We're going to drill down into this in a moment. Our SC translator function that I mentioned earlier, that's able to map structured exceptions like access violations, for example, into whatever we want, basically, like C++ typed exceptions, for example. This is how the API looks like for the callback that you have to provide. And you can handle lots of types of structured exceptions. I just listed a few here because it doesn't fit the slide. We can have detect overflows and other hardware faults that happen. I think the most exciting one on this list really is the access violation that I'm sure it's most probably going to affect people and cause bugs. And for example, we can see here that we can again extract the exception record from these exception pointer structures and the exception address and construct the information from there. And if we go down a little bit down this rabbit hole and see how we can decode this rich information there, we can see right away the exception code. That's the easy part. Those are just some defined codes that the C runtime defines for this. And for example, if we just focus on the access violation type, then we can assign special meanings to the data members in these structures and see what information they give us. For example, the operation type is just this position 0 in this 2-element array, and the operation type is either a read or write or a data execution prevention block that the operating system enforces, for example, when trying to execute data. So we have the operation type here, where we can switch on the operation type and see if we have either write or read. We can have the virtual address, which where the fault occurred. So the actual virtual address of the faulting location where the memory was accessed. And we can see if for example, if the virtual address was null or not. It was actually either a null pointer or not. For example, if we try to read or write a null pointer or a dangling pointer that it has a particular value. And by just examining all these combinations, we can construct and decode the type of issue that occurred in this particular access violation. Like we've seen earlier in the very first StackTrace, where we had this information on hand. So it's once you know the meaning of these structures and their fields, you can easily see what happened there and construct information to be recorded or logged. And we have a helper function here. Let's call trace from context. And we pass in this context record that we receive, and it does all the work of constructing the stack trace and the contextual information. And as for the location, again, this information can be mined from the context record. We have some helper function here, get exception origin, that will give us file name, file line, for the issue that occurred. And we can see how we can walk all the stack frames starting from this record all the way back to the very first module load address. And you can choose what to do with this information. For example, we chose to encapsulate all this contextual information that we extracted, to encapsulate it into a particular typed C++ exception that we called ACH exception, and you can throw it and handle it in some way, or you can log it, or it's up to you on how do you decide to react to these kinds of events. If you choose to let the application crash, or log the information, or archive it. Of all the options, I would say the least inspired one would be to just limp along and try to recover. That wouldn't be a very great idea. But there are situations where there are particular types of crashes where there are recoverable paths through your application or your process. It really depends on the particular context of the operation that you're performing. So at the very least, you can crash the process and log the information before it happens. So we end up with a regular C++ exception wrapping all this information, and we're going to see how we can construct it. But what happens if an exception is in flight? So, for example, to get the stack trace for the raised exception on the current thread, because threads really matter. So you can easily build an API for yourself to get the stack trace for a current exception. Again, using the same function that we're going to drill into, trace from context. You just have to get the current exception context. So when we installed an SE translator, this exception context was passed into our callback by the C runtime that runs underneath our application, our process. In case of catching the in-flight exception, that may very well be a C++ exception or any other kinds of SE translated exception. When you want to catch an in-flight exception, there's a way you can get this context yourself without the help of the runtime. There are some hooks there that can help you. So we have to have a way to get this context structure that we've received earlier for free from the runtime. And if we look at this context structure is quite awful. And honestly, not all bits are important, but I'm going to point you to some things that are interesting here. For example, you have the state of the registers, and these are mapped to what I talked earlier about the rich context on really understanding what happened in a deferred way. So just as if you would stop on a breakpoint on a particular crash or a particular point as you debug an issue live, and you see the memory window and you see the registers and see all the contextual information that you have right away at your fingertips while you're debugging live. The very same thing can be neatly packed with all the information without losing anything and archived to be debugged later. So I think there's great value in that. The exception pointer structure that we've seen earlier already in a translation function, we see that it has a member that is a context record inside, and we actually accessed it earlier. So these exception records are implemented slightly differently depending on architecture. For example, on x86, there's a linked list of these structures. On 64-bit architecture. There's a more efficient way of having a table of these, a lookup table for these exception records, so that the price you pay for these functionalities is lower, and you have better performance on 64-bit when dealing with structured exceptions. So they sort of look binary compatible, but they have different semantics in how they are organized within, and you can easily abstract away this information when you build your helper functions. So how do we get this p context, this pointer to a context? And this is where the bits get hairy, but you have to trust me that this magic incantation works. There's different ways because the C runtime changed dramatically. So if you're dealing with a newer versions of Visual Studio, like let's say 2015 and newer, then these would be the C runtime APIs that you need to call, and some of these symbols are private, so don't worry about that. Just consider it like a magic incantation that you need to wrap around in this helper function that you just use. For older Visual Studio versions, if some of you are still interested and need to reach out to that, we had another implementation there, slightly different functions from the CRT, basically achieving the same thing. Again, we have to differentiate between if we actually do static linking to the C runtime or dynamic linking to the C runtime. So depending on how you build your application, if you statically link to the CRT, or you actually rely on it as a separate DLL, then you have to access this information slightly differently to slightly different CRT functions. But ignoring all those messy bits, and by the way, these APIs, some of these APIs are private APIs, but there's easy ways to reach for their prototypes if you include the right system headers there. And I've just shown this here for completeness and ways to get to be able to actually reach these symbols and link against them. So getting back to these structures from the CRT, this is where the CRT power comes into that we rely on. And we see here in this structure that we have the context information, the current exception, we have the install translator in place, and all sorts of other useful information about the image, the connected image, and frame information for the current stack frame. And that would be very important when we start to walk the stack to construct a stack trace with all the information at each step. So Another useful scenario that we found is we want to stack trace from a particular context of the caller. For example, no crash occurs, no exception is in flight. At a particular point, you just want to log information to see, for example, we have a particular function and we want to see all the ways that function is reached. For example, all the paths through which that function ends up being called. And maybe you want to record that information to build a better understanding of hotspots, hot scenarios, or most frequent access patterns to a particular function outside of actually benchmarking, because then again, benchmarking instrumenting the application, it's a live process. You want to see this information maybe deferred, so offline. So how do we get this P context where no exception is in flight? Again, trace from caller is an API that you can easily build yourself by just wrapping this call to RTL capture context, which is a WinNT API that you can easily call. And from there, we reach out to our friendly trace from context function that we haven't seen yet implemented, and just provide that context, and it just builds the same contextual information for us. So we've seen this helper function trace from context many times by now. How do we walk the stack? How do we get from this P context wherever we got it from? Either the ASC translator or the in-flight exception, or maybe we just started from a particular point that we chose ourselves. How do we walk the stack? So first of all the debug help functions, such as stack walk, are single-threaded, so you need some way of synchronizing access to this kind of thing. So multiple threads and multiple exceptions in flight in multiple threads can happen. So you need to take care that you don't mess up your context information when doing this translation. So you get this context information, you have the current process and current thread information, and you have a way to explore symbols. And there are two parts of the stories. On the one side, you have the processing that happens on the client side, where crash occurs, and where you don't have the symbols on hand because you want a lightweight real release deployment. And a similar workflow where you have to basically replay your steps and debug the application on developer machine offline deferred information, using that archived information of the crash report without the symbols, and accessing the symbol database that you have on premise. So basically the same infrastructures and the same steps occur, but on different sides of the problem, either on the side where the crash actually occurred, or later on when you're trying to rebuild this information and start debugging it. So again, this is where things differ in terms of how you access the symbol information. And we have an init stack frame from context helper that we're gonna drill down a little bit into, and the main part of this function is this for loop that we just use to inspect each stack frame starting from our given context. So we use the stack walk API here from Debug Help Library in Windows SDK. And we just stack walk each frame until we either exhaust the frames or we reach a maximum frame count that we have imposed here. And at each step, we have a helper function that helps us compose stack frames. And at each frame has a particular address. We can see here from the stack frame, we have a new structure here, which is stack frame. And this structure has an address PC. So this is the program counter, and it's offset. So this is the information that we need from this particular stack trace. We need the particular its address basically. So this would be address PC offset. And each time the API is called, it just moves along and loads a new stack frame in this current current running structure. So at each step, this API fills in new information in this stack frame structure that's marked in red on my slide. And at each step, it fills in the context information, which is the blue variable here, context. And we also need another piece of information here, which turns out to be very important, which is the module base address. This is relevant because newer compilers actually use by default ASLR, which is address space layout randomization, which prevents loading modules at predictable load addresses within a host process. This is to avoid hijacking and trampolines and other means of exploiting processes. So each time a particular process loads its modules, it would load them at different altitudes in the virtual space of the host process. And when we have to run this framework ourselves, we have to record for each run where the crash occurred, we have to record this module base address, because all the addresses that we actually record will be will have to be translated relative to this module base address. And when we actually debug the application later on offline, we'll have a different module base address, of course, and we'll have to do some address offsets translations in order to get correct offsets into the PDB information database. So that's why we need to archive this information as well. Prior to ASLR, this wouldn't be an issue. But it's an easy translation to make. Very easy once we have the information. We've seen in each stack frame from context, this is the way how to initialize that new stack frame structure that the SDK gives us from the context. So we need to store, we've seen address PC, that's a program counter there. And we see that we have to load from the context, we have to load the EIP and EBP and ESP registers and set the address mode to flat addressing. And this is different on 86 and x64 and ARM, but it's fairly similar. So the changes are mechanical, just the registers are different. This is how it looks like on 64-bit, for example. We just use the wider registers. And on ARM, it's just different registers. And compose module base address. This one is very easy. Just one simple API, get module handle. If you pass it a null pointer, it will give you this module load address, so the very first load address of the particular module that you call this API from. So this is the easiest bit of all. This is how you get from that dry information, you get all this running through the symbolicated tool and get the rehydrated rich crash dump from your application. So one important bit is that this standalone symbolicated tool must come into instruction set architectures to match the debugged process. So you have to have both a 32-bit and a 64-bit version because you actually attach sort of like a debugger. So the way you are able to reconstruct this information when you're doing it offline, you have to launch this symbolicated tool and launch the process that you're debugging, your application that is. And it's launched in a particular way. It's launched as if it's being run by a debugger. So the symbolicated tool acts sort of like a debugger, and it needs to match the architecture of the debugged process. Again, we have some helpers there for dealing with PE images. If you know about Windows binaries, you know about portable executable and COFF formats for binary formats of executables and DLLs and object files. So you have to have some utilities to help you deal with binary images on Windows. And the StackTrace analyzer just switches how it operates based on architecture of the particular image. So you have to look at the image that you're instrumenting and see the architecture of the image and just switch on the correct execution path. By the way, you don't have to follow everything, all the code here on the slides. Some bits are really gnarly. The important thing is to get the idea and the mechanics involved in understanding how to construct this information, because the code is purely mechanical and just details that you can grab from the slides and it will just work. So don't try to follow along all the details. I'm just trying to highlight the important bits at each step. So as I said, you have to launch a sort of a debug session for this process you're trying to resymbolicate to. And you have to get this debug process base address, so the new load address of the module that you get from this process you're launching. And you have to initialize your symbol manager to connect to this information that we have archived, or those DSIM files that I've showed at the very start of the session. And then you just have the central point of the analyzer where you just say, symbolicate this crash report and get the context information back out with all the information as if the crash happened right now. So basically, all this workflow that you're doing on the developer machine, deferred offline, is just like simulating the crash really occurred now, rather than at the regional moment on the client machine. And the init process is just a simple setup for the ImageHlp library and the Debug Help library with sim set options and some flags. Don't worry about the details. And just initialize this for the current process and set the symbol search path. And this has to point to, I've provided all the links here if you want to drill down more. The symbol search path has to point to the place where you actually have those PDBs that I've shown in the DSIM files that we archive with our build artifacts. So this has to point to those PDBs, so that the loader finds those PDBs as it loads the debugged process and it starts up, and then it will just pick up this debug information as we walk each stack frame. You can dynamically load these APIs from the DbgHelp.dll, as I mentioned earlier. So you can choose to carry this DLL with you and load the APIs dynamically, or can statically link against it. Set symbol search path is just mechanical, so I'm not going to worry about the details here. I'm going to just skip it. And the symbolicate, this is where the actual work happens. So this would be the funnel of the operation, where you get all the frames. So you get all the frames from the crash report. You get the frame address, which is the first one, the first stack frame. The very first stack frame in the frame array is the crash address. No, it's the base address. Excuse me. So it's bottom up. Its array is filled bottom up. And then you just walk these frames and process each frame at a time. So I've highlighted here all the functions that delegate this information separately. This symbolicate API would be just the funnel that orchestrates all the process. And the process stack frame helper just deals with a particular stack frame. I've shown this here in this for loop. So it just takes the current stack frame, it gets the frame address, which is just a pointer. If it's the module load address, so the base address, it does nothing. If there's no symbol at that location, again, has nothing to do. And this is where the translation occurs, the one I mentioned earlier about ASLR. So you have the frame address that is recorded in the StackTrace, in the crash, and you have the debug process base address, which is the current load address, and the StackTrace base address. the one that is recorded in the crash dump. So this is the recording in the crash dump. This is the live one happening now. So you just have to address these offsets and just compose the stack frame. And the composition here is fairly mechanical. I'm not going to go into details here because I just left this information so you can play around with it if you copy code from the slides. Again, dynamic ways to reaching out to these APIs. I just left them here for you to have a way to actually play with this code, because if you copy paste the code from the slides, it will actually work. It's not just slideware. And the location information, again, there are APIs in the Debug Help Library. Sim get line from address. You just give it the virtual address, and it gives you a displacement structure and an image help line, file name, file number, and etc. Easy, nothing fancy here. So all the heavy lifting actually occurs in this DLL, Debug Help DLL, which comes with the Windows SDK in 3 architectures, and you can just reach out and inspect this documentation. So this is actually public documentation, so you'll find plenty of resources on docs.microsoft.com about how to use many more functionalities from this DLL. So we've seen how to build our own, but there's a good in-the-box alternative if you don't want to mess with all the details. And I think this is a really game changer. Visual Studio and newer versions of Visual Studio 2019 have revamped mini dump file functionality, which is called the VS snapshot file, and it's a real game changer. And it's a way to basically achieve the same things I showed earlier through Visual Studio, but you have to be on the latest and greatest versions, really. And it's amazing, the experience of actually using it. So we can basically achieve the same things I've shown how to build manually. It can be handled through these new revamped mini dump files in what they call the snapshot file that you can load in VS and start a debug session right away, as if it happened right there and then. And you can even combine it with live share and debug collaboratively if you want. So it's really nice. This is how it looks like in the IDE, and the live share feature if you like that thing. And a glimpse of what's coming into standard C++. We have an actually old proposal by now that sadly didn't make it into C++ 20 for time constraints. We have this 88.1 proposal. And we have a way of naming is hard. So it's hard to standardize on whether you get a StackTrace, backtrace, stack frame, and other names. So looks like we're probably going to get StackTrace as a name. So key features desired: all functions have to be lazy. You want to query the StackTrace entry without an explicit request. Of course, you want a dynamic size for the trace. So implementations can allow disable, enable of gathering stack traces by a linker switch, so you don't have to pay for what if you don't want this functionality. And all this functionality doesn't have to inhibit optimizations. So any extra information that is recorded or inserted into the binary mustn't prevent optimization that can occur, and should be usable in a contract violation handler, coroutines, handler functions, in all contexts that you might desire. So it must not have limitations on where it can be leveraged. So the description method should return the mangled function signature. The toString helper for StackTrace should query information from the debug symbols, exactly like I've shown earlier. And symbol tables and other resources must return the mangled signatures, of course, because they would be pretty useless otherwise. And information about inline functions that have no separate StackTrace entries is welcomed, but at this moment I'm unsure how this will be handled in different implementations, or if this would be in any ways required by the standard. and avoid heavy operations in the constructors of the StackTrace class. Or the way to get the current StackTrace entry, which is this static function current. The StackTrace entry class would have a way to get to the native handle type, just as you would with standard thread, for example. And it will have the most desired functions, description, source file, and source line. And that's pretty much it. You don't get any other rich contextual information, for example, the state of the memory or the registers at that particular time. So it's fairly limited, but it's good enough for most purposes. And the StackTrace structure it would have some sort of a vector of these frames that we've seen earlier, and the way to traverse them using the classic iterator pairs there. So the way to reach out and get a hold to a StackTrace would be to invoke the current static function, and there are various overloads, of course, and support for allocators and everything, but because these functions need to allocate memory to store all this information. So this is a way you would get the current evaluation in the current thread of the execution and get a hold of this array of frames that you can traverse. And traversal is fairly easy. You have various overloads for the toString method to give it either a StackTrace entry or a StackTrace as a whole. And you have IOStream operators to make it really easy to log this information. You can traverse it with a range for loop, for example, and get a description, source, file name, and everything. You can directly invoke toString on particular stack frame entry, and it does basically the same thing, but you don't have any control over the formatting. So it decides how it wants to format this current frame. Or you can just use the stream output operator, which does the same thing. Basically, it's identical. Or you can just invoke toString directly on the whole trace and just does what the implementation wants it to do and how it wants it to format it. So you can choose the level you control you want to have over this in terms of formatting and how you want to extract all this information. It's you can even use the output stream operator directly. So it's it really cannot get any simpler than that. So it will be a very easy to use API, and I'm hoping this will push people to actually use it, because it will be easy. It's limited. It's more limited than what I've shown and what we constructed from scratch. But I think it's good enough that for most usual scenarios will encourage people to actually deal with this and replace custom-made implementations with the standard one that we're going to get in C++23. So I'm excited that this is going to be now part of the mainstream vocabulary for how to deal with crashes, and I cannot wait to see early implementations of this. So I think we're almost at a time point here. So if you have follow-up questions, I am going to address it. I see some questions here, but are are related to client power tools rather than the StackTrace issue. So if you have follow-up questions, do reach out to me in Remo, and I'll probably be on the at the follow-up tables or somewhere at some tables somewhere. So just reach out to me, and we're gonna pick it up in Remo. Okay, I'm looking forward to seeing the rest of the talks today and chatting with you people. Bye.